Thanks for the introduction, and thanks to SAMSI especially for organizing this excellent workshop. It's really a pleasure to speak to this group of people interested in deep learning and allied fields. So my talk is going to, as you can see from the title, is going to pertain to regularization methodology in a broad sense. And I will touch upon deep learning, but it's not going to be the entire part of the talk. So here is a brief overview slide just to set the tone. So if you are working in the field of Bayesian statistics, global local regularization probably will not need a huge amount of introduction to you. If you are not, then fear not. I will introduce the basic ideas and how they are related to what we plan to do in terms of complex and deep models. Okay, so the caveat being that most of the results that are known to us, they pertain to linear Gaussian models. So it has been extensively analyzed, and the theoretical results are in place. The computation is well understood. In this talk, we are trying to go beyond. We are trying to, in particular, we will talk a little bit about the advances in complex and deep models. And complex could mean, deep models I guess is fairly well understood. Complex, what it could mean different things depending on the context. So in particular, I'm going to focus on nonlinear models, non-Gaussian models, and then I'm going to talk about deep models as well. In case you are wondering why the entire talk is not on deep models, what is the need for the other two? So my answer is twofold. The first reason being that this is a sort of this is an overview type of talk. I'm going to touch upon my own work as well as other works that I feel are going to be relevant. And I don't think I have enough material just on deep models working on this methodology to fill a 40-minute overview talk. So that's the more mundane reason. And the second reason is that these features, nonlinearity and non-Gaussianity, we encountered them in deep neural networks. We encountered them with huge amount of regularity, right? So my hope is what we are going to be talking about in this presentation will set the field for will set the tone for something that we can not only we have done, but we can do in the future. I will be in SAMSI for the fall semester as a research fellow. I will be leading one of the working groups. So I'm really hoping some of the material can be useful for our future discussions. Before proceeding further, this is a lot of it is joint work with Jyotishka Datta, who is in Arkansas, PhD student Yunfan Lee at Purdue, and then Nick Paulson and Brandon Willard from Chicago Booth. We are supported by NSF DMS for this work. Okay, so here I will just set the tone for global local regularization. And our the model that I'm going to start with is the simplest possible model that you can think of. That's the so-called Gaussian sequence model. So you have conditionally independent observations, yi given theta I. These are conditionally, not marginally, but conditionally independent with mean theta I and standard deviation 1. And you have sparsity in a certain sense, in the sense that the number of non-zero terms is upper bounded by this Pn, which is little o of n. Okay, so you have a lot more zero parameters than you have non-zero parameters. And if you are taking a Bayesian approach, it's natural to say that, well, I believe that there is a lot of zero in my model. So what am I going to do? So I will put sort of a spike or sort of a non-trivial probability of parameters being 0. And then with that will be some with probability p, and with probability 1 minus p, my parameters are allowed to take other non-zero values. So that's fine. But the computation, at least if you are interested in sort of exploring the full posterior, which is one of the goals of Bayesian statistics, then it becomes very, very challenging because you have to sample all this bunch of discrete indicators and things like that. So the global local regularization approach is a way to get around that. So you can put the prior in while working with entirely continuous random variables. Okay, so everything is continuous, and you can do batch updating of parameters, and a lot of computational challenges in exploring the posterior is alleviated with these priors. Okay, so this prior looks it's a sort of a Gaussian scale mixture prior, and so we assume that the prior on theta given these two parameters lambda I and tau is normal with mean 0, and the variance part has this kind of structure, and this probably explains why it's called a global local prior. So these lambda term depends on I, So it's component specific. So that's the local term. There is no I in the tau term. So that's your global term. So the idea is that if you choose tau in a judicious manner, presumably you are going to pull all the terms close towards 0, because that's what you should be doing, right? You believe that your model is sparse. But if I shrink everything to 0, that's no good, right? Then my estimator is identically equal to 0. Then I lose all the signals. So I have to have some mechanism so that the signal terms, the true signal terms, can escape from being overshrunk. And that is accomplished by these local lambda I terms. The key being we put sort of a very heavy-tailed prior. Heavy in this case means sub-exponential. Okay? So polynomially decaying prior on these lambda I terms. And what polynomial priors do is that they put a lot of mass near the tails, right? Less mass near 0, a lot of mass in the tails. So we rely on the tau terms to shrink everything close to a 0, but these lambda I terms help with the signals. Okay? So we can keep the signals. So that's the basic idea. So the global term tau should provide substantial shrinkage towards 0, but just to ensure that everything doesn't get overshrunk, these lambda I terms they need to have heavy tails, and with Cauchy being one choice. And here I have deliberately written p lambda I and p tau to denote some generic density to underscore the fact that there is not one unique choice for p of lambda I and p of tau. In fact, they have been explored extensively in the literature over the last 10 years or so. So the first work in this domain that I am aware of is the Horseshoe prior paper by Carvalho, Paulson, and Scott that appeared in Biometrica in 2010. And since then, this prior and related priors have been extensively studied, at least in the case of linear Gaussian models. So here are some of the other examples. So we did a little bit of variation on the Horseshoe prior that we call that the Horseshoe plus prior, that is even more heavier tailed than the original Horseshoe and even sharper, has even stronger pull towards 0. So we call that the Horseshoe plus. David Dunson has done a bunch of work. The generalized double Pareto prior and the Dirichlet-Laplace prior of Bhattacharya. David Dunson is in this paper as well. And finally, Mala Ghosh and Ray Bai from University of Florida, they came up with the inverse gamma prior. So these are the various priors that I'm aware of, some of the more prominent examples in the literature. But they all share this common feature of a strong pull towards 0 and heavy tails. Okay, so the strong pull towards 0 help with the sparsity. The heavy tails help with retaining the magnitude of the signal terms. If you are interested in what these priors look like, it's quite intuitive actually. They look like this. So you can see that this part here, this is the density is actually unbounded at 0. So this is while being continuous, this is approximating the delta function or the spike at 0, and the tails are actually quite heavy. So if you can read, this is the lowest curve here is the normal. So all these priors have heavier tail than normal. In fact, they all have heavier tail compared to exponential as well. So this part is helping with the sparsity. These tails are helping with keeping the magnitude of the signal terms. So that's the basic idea. Okay, and these things arise as the Gaussian scale mixture. So what we are seeing here is the marginal prior on the theta I term. Theta I conditional on lambda I and tau is normal, but the marginal prior on theta I is not normal. So what we are saying here is the form of the marginal prior. So why are these priors so popular? So for good reasons actually. So they have been extensively studied in the case of linear Gaussian models. So I have tried to list some of the this is by no means exhaustive, but some of the prominent works. So Datta and Ghosh, J.K. Ghosh, Janta Ghosh proved that so if you are suppose you are interested in classification, so you you are interested in classifying zeros as 0 and non-zeros as non-zero, then the error rate that you get from this prior is actually asymptotically optimal. Okay, it's asymptotically optimal under 0-1 loss. So that's very good if you are interested in classification. What if you are not interested in classification, but you are interested in estimation? So then the 0-1 loss doesn't make sense. What makes sense is the L2 loss. And on this problem, Stephanie van der Pas and Art van der Wart from Leiden, and they have worked extensively, and they have 2 papers in EJS, Electronic Journal of Statistics, that proved that the Horseshoe estimator that you get, the posterior, if you use the posterior mean as the estimator, that's actually asymptotically that's minimax in L2 up to a constant. We have a recent paper in JMLR, so where we sort of moved away from the asymptotic domain. We tried to focus on what can we say about finite sample risk properties. Okay, the first two results are about asymptotic risk, so you have to let n go to infinity and p go to infinity as a function of n. So the third paper is just finite sample risk result, works for any n and any p larger than n. So we studied, we showed that under certain cases you can actually beat ridge regression and things like that in finite samples. If you're interested in what kind of results are out there in literature on these kind of priors in linear, at least in linear models, we have a forthcoming paper in statistical science. So that's so it sounds very good. But then what have been done? So with these background, then what can we say about the existing results in nonlinear, non-Gaussian models? Because our ultimate focus is deep neural networks, so we have to handle nonlinearity, we have to handle non-Gaussianity. Okay? So here is the first foray into that. So we'll start out with some of the nonlinear estimation problems. So again, so here, so what we did is that in our 2016 paper, we considered 4 of these nonlinear problems. So again, your starting model is yi given theta is normal with mean theta I and standard deviation assumed to be known. But our parameters of interest are no longer the original theta i's. Instead, they are the sum of squares or the maximum of theta or theta 1 times theta 2 with the remaining thetas being nuisance parameter and so on. So each of these 4 problems, it's clear that they are nonlinear. Okay, they're nonlinear. And then what we showed is that even if you, even with under these nonlinear transformations, you still get good results. Good in this case being non-informative, meaning the data can really speak. The prior is not you really get some sort of a non-informative Bayes answer for these 4 problems. So you get good results under the horseshoe prior on the original theta. And the reason being, these local lambda I terms, they still leave the large signals unshrunk, even for psi 1, psi 2, psi 3, and psi 4, when these are your parameters of interest, not the original thetas. And the global terms still help with the noise component. So the question is, why does it happen, right? There is no reason, if it happens for the linear model, there is no reason why it would happen for nonlinear model. So the key property is actually regular variation. So remember, our prior on the lambda is half Cauchy. So that has a regularly varying or a polynomially varying tail. And as it turns out, in each of these 4 problems that you see, these transformations, they all preserve regular variation. If the prior on the original theta I is regularly varying, the induced prior on each of psi 1, psi 2, psi 3, and psi 4 will also going to be regularly varying. And that actually helps, because if the prior is regularly varying, so the prior dominates the likelihood, right? The likelihood is still normal. The prior has heavier tails than the likelihood. So the answer that we get is actually it's a 2-page Biometrica paper by Phil Dewitt in 1973. Is that in this case, what will happen is that the data will dominate, the prior will not. Okay, so that's the main reason the horseshoe prior works really well even for these nonlinear problems. Okay, so that's nonlinear. Moving on. So yeah, so this actually resolves a long-standing difficulty first noted by Efron, who pointed out the fact that it's actually very, very difficult to design a single prior that will work well for all 4 problems. You can certainly do well if you design individual prior for each of these problems. But designing a single prior on theta that will give good results for 4 problems is very, very difficult. Okay, and that was noted by Efron in the discussion to the marginalization paradox paper by David, Zedek, and Stone. So in some sense, our work resolves that difficulty a little bit. So the performance is quite competitive with reference priors. When these priors exist, reference priors are not guaranteed to exist, remember. And global local priors are proper. These are proper priors. They integrate to 1. So there is no difficulty with model selection and things like that. They can proceed in the usual way. Right? So that's about a nonlinear model. So what about if we move on to non-parametric models now? Okay, from nonlinear. So this is not our work. This is Min-Suk Shin and Anirban Bhattacharya and Val Johnson from Texas A&M. So what they did is that they handled the non-parametric regression model. Okay, so it's a very standard setting. So yi is f of xi plus epsilon I, where f is some function that you are trying to approximate. So a standard way would be to just write down a basis function representation, right? So you appeal to Karun and Loewe theorem and say that, okay, I'm going to have a k component basis function expansion. And then you can think that, well, so then how about I put sparsity prior, regularizing prior on these beta k's. But that actually doesn't really make much sense if you think about it. If suppose I make some of these beta k's 0, right? Well, some others are non-zero, and what you get, this f is a linear combination of some other basis functions which have not been shrunk to 0, and it's not clear what that shape is. So what they did is actually not that. Okay. So what they did is that they, as Bayesians, they had prior belief of f, this capital F, being close to certain parametric family of functions. So you might have a prior belief that this capital F is close to linear or close to quadratic. So then it makes sense to shrink toward that shape rather than putting some sparsity prior directly on this beta case. And that was the idea. So that's what they did. So they call that prior the functional horseshoe prior. Okay. So if you have, we define phi 0 to be the column space of the parametric function that we want to shrink to. So an example is that if you want to shrink towards linear shape, then this phi 0 will be 1 comma x, right? So 1 for the intercept, x for the linear term, and that becomes your phi 0. And then given this phi 0, the prior on beta is defined in this way. So again, you can see that this is beta give the prior on beta given tau. That's a normal, right? This is a Gaussian kernel in beta. This is a Gaussian kernel. And what you are doing is that this part inside phi transpose I minus q0 times phi. This is really the sigma inverse term, right, in the Gaussian kernel. So what you are doing is that, and here there are some other terms to define, some equations. So d0 is the rank of phi 0. So in this case, in this example, d0 will be 2, and q0, this q0 that you have over here, I minus q0, this is the projection matrix of phi 0. Okay. So q0 is defined in this way. So what is happening really is that in this way, so basically this I minus q0 term in the prior inverse covariance, this is the part that's enabling the shrinkage of phi towards phi 0, right? So when is this term 0? So if I is q0 is exactly equal to I, then this term is 0, and that's when you get the maximum contribution to the likelihood. Otherwise, you get lesser contribution. So how is this related to horseshoe? So there is this additional parameter tau, and they put this kind of prior on tau, which reduces again to half Cauchy for special values of a and b. If I put a equals b equals half, then the prior on tau is precisely the half Cauchy prior. Okay. So in this way, this prior is related to the horseshoe prior, and they called it the so-called functional horseshoe prior. So this is very good because they established model selection consistency in non-parametric regression with this prior, and they showed very, very good empirical results as well. Okay. Okay. So we have covered nonlinear, non-parametric. Let's move on. What if your data shows some dependent structure? So far, our observations, these yi's, have been, if not conditionally independent, if not independent, at least they have been conditionally independent, marginally exchangeable. But if you have some dependent structure in the data, what to do then? So Daniel Kowal and others in their just recent JRSSB paper, they actually showed that if you define, remember this tau and lambda I, these are the global and the local parameters. So they do what they do is that they don't put prior on half Cauchy prior directly on tau or lambda I. Instead, they take log first. So it becomes log tau square plus log lambda I squared. That's their mu and eta I. And then they showed that if you put the Fisher Z prior on these eta I terms, that actually induces horseshoe, basically half Cauchy prior on these HI terms. So that's good. So far up to here, it's only just the basic horseshoe, just a reparameterization. Then they introduce dependence in this way. So they just make this HI term, instead of having a vanilla mu plus eta I, global plus local term, introduce dependence by putting this kind of autoregressive structure. So in this way, so this is, you can think of this as related to the sort of the arch type of model, okay, except that this is global local. So this is very, very good because oftentimes we have to deal with dependent data, and the priors that we showed earlier, they are just not equipped to handle with dependence in the data. All right. So the canonical example that is in trend filtering. So trend filtering, basically, you can think of it. There is some analogy to moving window averaging. So, but there when you have dependent data, so that's what they showed their application to, and it produces excellent results. There is a very, very similar formulation by Bito and Fruwart-Schnatter in Journal of Econometrics. They use a slightly different prior that they call a double gamma prior, but the idea is the same. Do not put the prior directly, take log first, and then put the prior. Okay. So nonlinear, non-parametric dependent models. Let's move on. What if your data are not univariate, right? So far everything is univariate. Yi, the noise term is epsilon I, that's Gaussian. But what if I have multivariate model? So in a canonical example will be something like this, right? So yi is multivariate. These are sample. I have samples not from univariate normal, but from multivariate normal. Okay. So the entire y is an n times p matrix. Yi's I going from 1 through n. These are samples, but each yi is a p vector, and I have a p by p inverse covariance matrix. And if I want to do network estimation, then sort of a natural assumption is that my inverse covariance matrix is sparse. So how do I? What if I wanted to do these kind of regularizing? If I wanted to use this kind of regularizing priors on the inverse covariance matrix, and as you can see, that now there are additional challenges, right? I cannot just blindly define priors. I need to maintain. I need to ensure that my estimate is symmetric. I need to ensure that my estimate is positive definite, and so on and so forth. So this is the prior that we used. So we just put there is no reason to particular reason to shrink the diagonal terms. So we just assume that they are just proportional to 1, meaning just this is a priori. On the off diagonal terms, however, we put these kind of global local horseshoe prior. Okay, so these omega ij's are the elements of omegas, and this is symmetric. So the priors only need to be put for I less than j. The upper matrix, upper triangular part is symmetric to the lower triangular part. With the prior mass truncated to the space of positive definite matrices. So that has to, our estimation algorithm will have to ensure that. So non-informative prior on the diagonal terms, independent horseshoe prior on the off diagonal terms. And then additional challenge, as I mentioned, is that, yes?
What exactly are you treating
Omega ij's, the elements of the inverse covariance matrix, because I believe I have a sparse network structure. So the additional challenge is that now I need to maintain symmetry and positive definiteness. Otherwise, it's not, my estimate is not a valid inverse covariance matrix. So how do I do that? So it's actually, so if the naive sampling method doesn't work, so what you have to do is that you have to reparameterize it in some sense. And that's actually, that was done by Hao, Wang, and others in the context of Bayesian graphical lasso. So we use that. So basically what you do is that you partition this omega in this way. So you break it down into this, the whole thing is p by p, you break it down to this p minus 1 times p minus 1 block. This part here is just a scalar, and these are just p minus 1 times 1 vector. And then if you can reparameterize this thing in a certain way, and then sample the reparameterized version. So it's a 1-to-1 transformation, but the nice thing about this transformation is that now the sampling is very, very easy. So if so beta and gamma are just the reparameterizations of the original omega, and now conditional on everything else, it turns out the posterior of gamma is just a gamma. The posterior of beta is just a normal, and sampling is very, very easy. So the conditional posteriors of the off diagonal terms are normal. Those of the diagonal terms, these are just gamma. And there is another nice thing about this reparameterization, which being that if you start your sampling process if your initial estimate of omega is positive definite, so you can just start with some multiplier of the identity matrix, then it's proved that all the subsequent iterations will remain positive definite. Okay, so all your, and then your final estimate could be the average of Monte Carlo samples. So the sample average is going to be positive definite as well. So that's very nice. So this was not our this reparameterization is not our work. This was explored in the case of Bayesian graphical lasso by Hao Wang. So what we did, so there is a key difference. In lasso, you have these lambda ij terms. They will have a double exponential prior. In our case, these are heavier tailed, half Cauchy prior. So now there is this additional, there's a slight challenge that we have to overcome, is that how to sample these global and local terms. So in this case, there is actually a key reparameterization of half Cauchy that has proved to be very useful, and it is this. So if you have a half Cauchy, a marginal, if you have a random variable that is marginally Cauchy distributed, you can write that as a mixture of two inverse gamma random variables. And later on, when we move on to deep models, we'll see that this reparameterization is actually also key to most of the variational based methodology that has been developed for the deep models, that are trying to employ horseshoe. Okay, so half Cauchy is a mixture of two inverse gamma. So why is this helpful? So inverse gamma is self-conjugate, and inverse gamma is also conjugate to a linear model. Okay, so basically with this reparameterization, all our posterior samples are available in closed form. They are either normal gamma or inverse gamma, so the sampling can proceed using usual machinery. The complexity is order p cubed. We have MATLAB code available, and later on, very recently, we have extended this work to sort of the seemingly Zellner type, seemingly unrelated regression model where both the mean vector and both the mean and the inverse covariance is of interest. So I'm not going to. That's actually quite similar. So I'm not going to talk about that separately. But if you're interested, you should check out our paper. Okay. So multivariate model. Global local priors for non-Gaussian model. So non-Gaussian model is another key feature of several types of deep neural network. So far the likelihood has been Gaussian, either univariate Gaussian or multivariate Gaussian. What if now the likelihood itself changes to something that's non-Gaussian? So Data and Dunson, they showed that global local priors not only work in normal models, they also do great in when the likelihood is changed. For example, Poisson. Okay, so now your model, your data are count data. The y's are observations. So yi given theta I, these are count with so Poisson, the rate parameter of Poisson being theta I. And then they on the Poisson rate parameter, they just used global local prior. You can see that it has a gamma prior. The variance of the gamma prior has a global term and a local term. So this is actually, as it turns out, so what will happen is actually quite similar to what happened in linear Gaussian model. It will put a lot more mass near 0, and it will have heavier tails, which in the case of count data, what it will mean is that you have basically as sort of an alternative to 0 inflated models. You have a lot of zeros and some few very large counts. So if your data is like that, this is actually a very useful model to sort of 0 inflated Gaussians, 0 inflated Poisson and things like that. So they have been used in this way. They have been used. These priors have been used in Magnuson et al. And Pironen and Bhadra in probit and logistic regression models, respectively. What about what is the dimensionality that you can handle with this kind of prior, right? So now, so far, I'm trying to be fully Bayesian. So basically, I have to do MCMC. So is it really scalable? So the answer is it depends. So do you have some local structure that you can exploit in order to introduce parallelism into your problem? And it turns out for several cases you can, because all these lambda I terms, the posteriors of them, they are conditionally independent of each other. Okay, so they're all marginally they are not, but conditionally they are all independent of each other. In terms of computation, what it means is that if you have something like a GPU, you can basically do something like a map reduce. So in your map step, so you update all these local terms by sampling from their posterior in parallel. In the reduce step, you combine them to update the global term. And that was what was done by this paper in Terandin et al. Just came out in Statistics and Computing. They classify 1 million data points in several thousand dimensions in several minutes, like 10 minutes of running time, using horseshoe prior on the parameters. So the key idea is to use it's quite effective actually, is to use GPUs in order to parallelize the local scale parameters. So it's a sort of a map reduce framework. Okay, so now deep models. What has been with these things? Now, how does it pertain to deep models? So here, there are actually far fewer works compared to shallow models. Be they nonlinear, be they non-Gaussian, there are simply just not enough work. So that's maybe a good thing or a bad thing depending on how you look at it. We may despair about that, or we may recognize this as sort of window of opportunity that there are still things to be done. The key challenge. So the first question is why? Why are there so few works? Even though deep neural networks are usually they are heavily overparameterized with respect to what we actually observe, right? So everybody knows that. So the key difficulty really appears to be computational. So the Radford-Neal style full Bayesian inference is infeasible in modern deep neural networks because computation is too costly. So the usual workaround is to just go with some sort of variational Bayes approximation to the true posterior. So is full Bayes hopeless? I do not know the answer to that, but so far it's just not much existing work. So what has been done with global local priors in deep neural network? So by Ghosh and Finale-Doshi-Velez, so this is Nurip's workshop paper, and then Ghosh et al. In 2018 ICML. So what they did is that they use horseshoe priors for model selection in deep neural network, except that this prior is not really true. So that when they do the posterior inference, they don't sample from the actual posterior because that's just too complicated. So they do some variational approximation to the posterior. So the inference, so variational approximation is not unique, right? You can have for the same posterior, you can have various types of variational Bayes approximation. So what these two papers did is that they used the variational approximation technique first identified in the Neville and Matt Wann's paper in 2014 EJS. So that's a sort of a, you write the, if I remember correctly, it's a product of bunch of normal and gamma terms. Why is it normal and gamma? Because ideally it should be the product of normals and Cauchys, but remember what we just said earlier, Cauchy is a product of 2 inverse gammas. So in that way, it becomes a product of normal and gammas or inverse gammas, and then you can optimize the parameters really easily. So the trick is writing the half Cauchy random variable that you encounter with these global local priors as a mixture of two inverse gammas. Okay. There is this paper by Luiso et al. They actually establish very interesting work. They actually establish a connection between horseshoe shrinkage and dropout. So if you think about dropout, what it is doing is that it's introducing multiplicative Bernoulli noise. You set some parameters to 0. So they said that if you have global local shrinkage instead, it can be understood as some sort of a continuous relaxation of dropout. And dropout, we are all reasonably familiar with what it's trying to do. I believe the ideas are still at a preliminary stage. There is some connection, but proper exploration will probably still take a lot more work. So there's that. So when you have when your final output of the deep neural network is binary or count, you need further augmentation, okay, in a Bayesian setting. So what do you do is that so there is the work by Gan and Larry Karin and others. What they did is that so their output is binary. So essentially, it's a bunch of stacked logistic regression models. So, but as it turns out, that can be recast as a normal regression problem as well, except that you have to follow some data augmentation strategy. So they use the sort of the by now standard polyagama augmentation strategy for logistic regression models. So again, you can sample a bunch of polyagama random variables, and conditionally you can sample a bunch of normal random variables, except theirs is not just one single logistic regression, it's a bunch of stacked logistic regression. So it's a pretty neat paper. Recently, Wang, Paulson, and Sokolov, they have actually worked on a similar line, and they showed you actually don't have to do a stacked logistic network. You can have a bunch of link functions, such as ReLU or logistic or check loss at each layer, and for each of these types of loss functions, you can find the corresponding latent variable representation if you want to write the whole thing as a normal scale mixture. Okay, so that's and then they try to do inference using that. So that paper, I don't think it's published yet. It should be under review. So that's about the output. What about the input to your deep neural network? Okay, so suppose I am interested in a GLM. So I'm not interested in a linear network. I'm interested in a GLM. So a GLM, as we all know, has this form, right? So there is a link function G, and my assumption is that G inverse of the conditional mean of y given x is a linear function of x, right? And depending on various types of G, you get various types of GLM. You can get a logistic model or probate and things like that. But suppose I don't like this assumption that the G inverse of E of y given x is a linear function of x. I would like to introduce nonlinearity here. Not make it linear in x, but make it nonlinear in x. So one way of doing that would be by making x itself the output of a deep neural network. It will have what kind of nonlinear transformation it would be, probably very hard to quantify analytically, but it will definitely be some sort of nonlinear transformation of the input x. So that's what Tran et al. And Robert Kohn is in this paper. They did is that they introduced nonlinearity by replacing this x with the output of a deep neural network. So they call this model deep GLM. And where do horseshoe priors come in here? So again, they use horseshoe prior for estimating these parameters beta, okay, to achieve sparsity. So in this way, so the horseshoe priors have been used both for the inputs to the deep neural network as well as for the link functions, the nonlinear link functions that you encounter in various layers by introducing these kind of data augmentation strategy that I mentioned in the previous slide. Computational strategies. I'll end this talk with a few note on computational strategies. So computation-based computation is just hard, right? Because the focus is not on point estimate. The focus is on approximating the entire posterior. So inherently, the computation is more challenging. So even for linear Gaussian models, if you wanted to do MCMC, up until 2016, the complexity was order p cubed. So when p is very large, much larger than n, it's very, very hard. So there is this beautiful paper by Bhattacharya et al. That they proposed an exact algorithm, and the complexity was reduced from p cubed to n squared p. Okay, so the algorithm is exact, no approximation to MCMC, exact MCMC, the complexity is reduced. So when p is much larger than n, this is a 2 order of magnitude improvement. So, so now suddenly a lot of things that didn't look feasible in linear Gaussian models, they suddenly look feasible now. But I am unable, so maybe we are waiting for a breakthrough of that, like that in deep models. So full Bayes is still very hard in deep models, and it's probably likely to remain so in the foreseeable future. Almost all papers that are attempting a global local shrinkage in these types of models that are known to me at least, they are either using variational approximations to the posterior, or they are using various types of point estimation strategies. It looks like I'm almost out of time. So what I will do is I will end this talk with a list of a bunch of softwares. You probably cannot read this slide, but hopefully these slides will be made available after the talk sometime in SAMSI website. And if you click on the left, these are hyperlinked, so they will take you directly to the GitHub pages for these software implementations. So there is we developed MATLAB code for the graphical horseshoe for inverse covariance estimation and its extensions. There are the one that's trying to use horseshoe prior in GPUs. They have code using CUDA. There are various R codes as well. These are for shallow nonlinear non-Gaussian models. As far as deep models are concerned, there are also some codes available. So Doshi Falaise, they have their code, as well as the work by Gan and Larry Karin, and finally the work by Louiseau and Max Welling. They have some MATLAB code. They have some MATLAB code available. These are some. So this talk is based on a work that's currently under revision at International Statistical Review. Hopefully, it will appear with discussion sometime later during this year. And some of our other works in these using global local regularization strategy are listed on this slide. Thank you.